will start with where we left off in the last class. Namely, we were looking at Maekawa's algorithm for distributed mutual exclusion. Now, let us quickly recapitulate the algorithm and then we will see what are the problems with this algorithm. So, unlike the previous algorithms like Lamport's and Reichert-Agarwala, Maekawa's algorithm works by obtaining permission from only a subset of processes, not all processes. Like Lamport's or Reichert-Agarwala requires permission from all processes, Maekawa's algorithm requires permission from only a subset of the other processes. And that subset, for each process Pi, we have a request set Ri, and before it enters the critical section, the algorithm must take permission from all the processes in its own request set. And there are certain requirements about these request sets, and the first one is that the intersection of every pair of request sets must be non-empty. That is required because there must be some process which arbitrates between Pi and Pj, so that Pi and Pj do not enter the critical section at the same time. So, there must be some common person from which they have to take permission, and that common process is there in Ri intersection Rj, and that common process makes sure that permission is not granted at the same time to both Pi and Pj, and that's how this algorithm guarantees mutual exclusion. And we also have two performance requirements. One is that the number of members in each request set must be the same for each process. So, to enter the critical section, each process has to make request to only k other processes, and k is a fixed number. So, that means that the size of each of the Ri's are the same and equal to k. And also, every node participates in the arbitration of d requests, d other processes. So, that means that the overhead that each process has to go through in participating in the arbitration of other processes is also well distributed and equal for all process, and that number is d. So, each node belongs to d of those Ri's. Okay. And for Maekawa's algorithm, we create the request sets in such a way that k equal to d equal to root n. Okay. We have not discussed how we create the request sets, but we assume that the request sets that are given to us satisfy that k equal to d equal to root n. Then the algorithm works in the following way, that to request a critical section, the process sends request messages to all processes in Ri, and on receiving a request message, a process does the following: it sends a reply message if no reply message has been sent since the last release message is received. So, the status of each process is of the following types, that it has either replied to some process and is waiting for that process to release, or it has replied and already got back the release, so it is free now. Okay. So, it is either free or it has given the permission to somebody, right. Now, when a process receives a request, it first sees whether it is free. If it is free, then he says, okay, you go ahead and execute the critical section. So, it gives the permission, and if it is not free, that means it has sent the request to somebody, rather the reply to somebody, and then it waits for that process to which the reply has been sent to release the critical section, and when it is released, then this process says that okay, now you can go ahead. Okay. So, the reply message is the one which gives the permission, and once you give the permission to somebody, you cannot give the permission to another process until the reply has been received, until the release has been received. and for a process to enter the critical section, the process enters the critical section after it has received reply from all nodes in its array, right. So, this is fairly simple, and then to release the critical section, the process sends release messages to all nodes in array because it had got reply messages from all of these nodes in array. So, it sends release messages to all these nodes in array, and then on receiving a release message, send reply to next node in queue and delete the node from the queue. Now, note one thing here is that we have not specified in what way the next node in queue is selected, right, whether it is selected based on timestamps or just selected on the basis of arrival of the requests, right. We have not mentioned that. In fact, the algorithm is silent about that. If queue is empty, update status to indicate no reply message has been sent. Okay. So, then that process becomes idle. Now, this algorithm can lead to a deadlock situation, and we will see through an example how a deadlock situation can happen. Suppose I have processes Si, Sj and Sk, okay, and these have their own request sets. Now, remember that, so these request sets are Ri, Rj and Rk. So, in order to enter the critical section, Si must take the permission from all nodes in Ri, Sj must take permission from all nodes in Rj, and Sk must take permission from all nodes in Rk. Now, let us say that we have the process Sij in the intersection of Ij, we have a process Sjk in the intersection of Rj and Rk, and we have Sik in the intersection of Ri and Rk, all right. Now, when Si wants to enter the critical section, it will send out request messages. Let us say that Si sends out a request message to Sij, right, and at that time Sj sends a request message to Sjk and Sk sends a request message to Sik, and they all get their replies. So, this one gets its reply because Sij was idle, Sjk gets its reply, Sj gets its reply from Sjk, and this one also gets its reply. Now, what should Si do? It must now also take permission from Sik. So, it sends a request to Sik, but that request cannot yet be granted because Sik has already given a reply to Sk, right, and Sj, after getting the reply from Sjk, it must also request to Sij, but then Sij cannot reply now, okay, and Sk will also request to Sjk, but Sjk cannot reply now. So, now you see we have a deadlock situation because Sij cannot give permission to Sj until Si has released the critical section, but Si cannot release the critical section because it is waiting for a reply from Sik, right, but Sik cannot give that reply because it has given permission to Sk, but Sk cannot execute critical section because it needs permission from Sjk, but Sjk cannot reply to Sk because it has already given permission to Si. So, we have a complete cyclic wait where each of these processes cannot enter the critical section because they have got permission from one member, but not from the other, and each of these processes cannot grant permission to another process because they have already replied to one of them, right. So, Marquardt algorithm has this problem that it can lead to a deadlock situation, right. And now, if we assume that we have low load conditions and that deadlock is a very special situation which can only happen rarely, then what is the number of messages that we are having to send? What is the complexity? 3 into root n. Why? Because there are root n nodes and every node requests from its only on its own request set. So, it is 3 root n. Compare this with Lamport's algorithm where it is 3 times n minus 1, because you had to request permission from every node, right. So, from that to 3 root n is a significant improvement. And what is the synchronization delay? 2 into maximum message transmission time. Why? Why is this 2 there? Because it has to release it to the members of RI, and then one of those members of that RI will forward a reply to the next one, right. So, that is why it is 2 into maximum message transmission time. We have seen that the major problem is that deadlock can happen, right. And now, we are going to quickly see how to get around the deadlock problem. So, that can be broken by using additional messages failed, inquire and yield, which will be used to handle deadlock, and the message complexity then will become 5 times root n. Instead of 3 times root n, it will be 5 times root n, because we will have additional 2 more rounds of messages, right. So, the message complexity will be more than that. So, let us see how this deadlock detection and elimination takes place. We are going to go through this quickly. Later we will come back and study deadlock detection algorithms in more details. Then we will see that there are some generalized ways in which we can handle deadlocks in distributed systems. So, here we are going to do the following thing, that we will have, suppose we have this site SI which sends a request for the critical section to some node Sj. So, let us say that we have this. Now, suppose Sj cannot reply now. Why? Because Sj has given a reply to some Sk and has not yet got back the release, right. Now, what will happen here is that Sj will compare the timestamp of this request with the request that Sk had sent. Okay. So, if the timestamp that this one had sent, let us say that that was Tsj, Tsk k. Okay. Now, if it says, okay, let me rewrite this as Tsii, so that we distinguish between these two timestamps. So, when we compare these two, and if we find that TSKK has higher priority than TSI I, then what will Sj do? Sj will send to Si a failed J message. Okay, and this is going to happen when this condition holds. So, if Sj sees that Si's request is lower priority than the request which it has already replied to, then it will tell Si that look, you have failed because your request has lower priority. So, you will have to wait, right. I am not going to do anything right now, you have to wait, alright. So, that way Si knows that this request cannot be granted right now, because Sj has already responded to some request having higher priority, right. Now, let us look at the other situation which is similar to this, except that Si has requested to Sj with a request of TSI I, Sj has responded, has sent a reply to some Sk because it had received some request previously having a timestamp of TSKK, right. And now, the case that we are looking at is that TSI I has higher priority than TSKK. In this situation, what will happen is Sj will send a enquiry. So, inquire J message to Sk. Okay. What is Sk going to do? Sk will see whether it is already in critical section or whether its state is as follows. So, suppose it has so happened that Sk in turn suppose Sk has received a failed message. Sk has received a failed message from some site in its requesting set, right. If that has happened, then what Sk will do is it will send a yield message which is an indicator that look, I cannot enter the critical section now because I have got a failed message from somebody. So, I am releasing you, but my request remains because I could not enter critical section. So, what Sj will do is Sj will put, see Sj has a maintains a request queue. So, it will put Sk in that queue somewhere down the line it will put Sk, right, and assume that it has not responded to Sk, right. Now, if it has not responded to SK, then it is now free to send a reply back to SI. It could be SI or it could be any node in its queue having the lowest timestamp. So, it will send it to that, okay, right. Now, when finally again at some point of time it gets back the reply, it gets back the release, then after sending the release somewhere down the line again SK will be given a grant, okay. Now, let us first understand that this actually takes care, it breaks the deadlock, okay. How does it break the deadlock? Let us look at the deadlock situation once again. We had SI which had got a reply from Sij, okay, and Sij had a request from Sj, Sj had got a reply from Sjk, Sjk has a request from Sk, okay, and Sk has got a reply from Sik, and Si has a request for, this was the circular wait situation, right. Now, what is going to happen here? Now, let us say that without loss of generality that I's request is the smallest timestamp among the request of Si, Sj and Sk. So, let us say TSI I is the minimum timestamp request among all these three, okay. So, now what is Sik going to do? It got Tsk k for which it had replied, okay. Now, this one is a lower priority request, right, higher priority request, So, this will send a inquire, okay. Now, let us look at this side of the thing. Sj has made a request with Tsj j, okay. What is Sij going to do? It will compare this with this, and what will it do? Will it send an inquire to Si? No, it will instead send a failed message to Si, failed, right. It will send a failed message to Sj, right. Now, between these two, which one should we assume to be smaller without loss of generality? You just tell me. Suppose we say that Tsj j has higher priority, okay. So, we are saying that Tsj j is higher than Tskk. Now, when this request blocks, what will Sjk do? It will send a failed message here, right, failed. Now, what will then SK do? It has got a inquire message, but it has got a failed message. So it will yield. What will SIK do? It will enqueue this request and send a reply to SI. Now SI has got both replies, it will complete critical section and the deadlock is broken. It should also, no, it has got replies from both in its request set, so it just goes ahead and executes critical section. So SI will execute critical section and come out of this, and therefore the deadlock is broken. Okay. Now see, in any cycle there will always be some process which has the lowest timestamp, and therefore that one will break out of the deadlock and complete. Then also it should not have been a problem. Let us look at that other situation. If TSK was higher than TSJ, what will happen? When this is done, okay, then this having higher priority, there will be a enquire message which is sent to SJ. SJ has a failed already, so SJ will yield, okay. Now is that clear? SJ will yield here, so there will be an enquire message sent. Let me use a different color. This will send a enquire, and then this will give a yield, right. When it gets a yield, SJK will send a, this will not happen, SJK will send a reply. Now SK has both, so SK will execute and break out. SK won't send the yield. No, because it does not have a failed message. So if somebody has reply from both, then it will execute. No, it is not always fair. It is not always, it is fair in the sense that everybody will get, there will be no starvation.
But the lower timestamp will have before execution, that kind of.
No, that's not guaranteed here.
That's not
no. Is it clear? Okay. Now, so far all the algorithms that we have seen are permission based algorithms, where we had to take permission from nodes to get into the critical section. Okay. Now we are going to move into a different class of algorithms which are token based. Now the general philosophy of token based mutual exclusion algorithms are that whichever process has the token is able to execute the critical section, and the token is passed from node to node, right, and we somehow queue up the requests in such a way that the token passes fairly. So let us look at this algorithm. So there is a single token which circulates, enter critical section when token is present at a node. Mutual exclusion is obvious because only one token is there. So it cannot be the case that two processes enter the critical section at the same time. There is an interesting variant, of course, that is in large distributed systems, if the token gets lost or a process crashes with the token, right, then a new token has to be regenerated, and that regeneration of the new token in a distributed manner can potentially lead to a situation where two tokens are generated, right. So those are very special scenarios which in the context of other kinds of algorithms we will study later on, and see that how that we can avoid that. algorithms differ in how to find and get the token. That is the main thing here. It uses sequence numbers rather than timestamps to differentiate between old and current requests. The first algorithm that we will look at is called the Suzukikisame algorithm, which is a token based mutual exclusion algorithm. So, broadcast a request for the token, that is how the algorithm starts, that a process which wants to enter the critical section will have to broadcast a request for the token. It has to broadcast because it does not know where the token is. So, it has to send a message to every node saying that I want to make a request for the token. Now, the process which has the token sends it to the requester if it does not need it. Okay, that is broadly what happens. What are the issues that we have to deal with? We have to deal with current versus outdated requests. So, it should not be the case that I made a request, I got the token, entered the critical section, then passed on the token to somebody else, and my request reached so late to that process that that process thinks that I want the token again. See, I broadcast my request to everybody. Okay. My request to him was so much delayed that by that time I had got the token from him, done my critical section, and then passed on the token to somebody else. Now, when he gets the token, he thinks that I want it again, but I do not want it again, right. So, that we have to be sure about, that we are able to differentiate between current requests which have not been served and outdated requests which have already been served. Okay. Determining sites with pending requests. So, the next issue is to find out when requests are pending and deciding which site to give the token to. Okay. These are the three issues that algorithm has to deal with. Right. First, the data structure. The token is a data structure which contains two things. One is a queue, a FIFO queue of requesting processes. So, the token has a queue of requesting processes. Wherever the token traverses, it carries that queue with it. Okay. And then there is another array called the ln array. Okay. I will explain what this is. lnj is the sequence number of requests that j executed most recently. Now, each process numbers its requests like 1, 2, 3, 4. So, they are the sequence numbers. Okay. So, process pi makes request 1, request 2, request 3, request 4. Process pj also makes request 1, request 2, request 3, request 4 and so on. Okay. Every process's requests are numbered, and this array ln1 through n is an array which records the sequence numbers of the requests that were executed most recently. So, if lnj is 5, we know that for process j the requests 1, 2, 3, 4 and 5 have been served already. Okay. If ln9 is 7, that means for process P9 requests 1 through 7 have already been served. Okay. The request message that is broadcast from the requesting process to all other processes also has a sequence number. So, when node I makes request for its kth critical section execution, it sends out the request I comma k message, right. Now, note that at a given point of time in a process Pi, there can be at most one pending request, because in critical section request you execute the critical section, then you make the next request. You do not pile up 5 requests. Okay. So, whatever has been served most recently and whatever is pending, that gap between the two can be 1 only, it is not more than 1, right. So, if 5 requests have been served for process Pi, then it is only possible that the 6th request is waiting, but it can't be that 6th, 7th, 8th are waiting, that cannot happen, right. Each node maintains a data structure RNI 1 through n, where RNij is the largest sequence number received so far by I in a request message from j. Okay. So, each node, whenever it gets a request, it keeps track of whatever request it has got, alright. Now, it is also not difficult to see that is it possible that you get more than one request pending requests from j? No?
In that case, it can be accepted multiple requests by j.
Now, see, let us understand, this is a very important point, we have to understand this very clearly. When I am sending you a request, it is not mandatory that you receive the request before I get the token, right. It may so happen that the token is with him and he gives me the token and I enter critical section. At that point of time, you may not have received my request, right. And after giving out the critical section, after executing the critical section, releasing the token, I may have sent another request. Now, that request reaches you earlier, so it is possible that that happens. Okay. It is possible that that happens, but in my queue I cannot have more than one request pending, because I will execute one and then only make the request for the next one, right. Now, no. Now, this is the algorithm. To request critical section, if I does not have the token, then increment RNI I and send request I RNI I to all nodes. Okay. Now, this is the situation where the process making the request does not have the token. Then it increments RNI I, because this is a new request, and sends this request to all nodes. On the other hand, if the process making the request already has the token, then it will enter the critical section. If the token is idle, that is, in the tokens data structure there are no pending requests. Okay. The token is idle if in the tokens data structure, the tokens queue, there is no pending request. Otherwise, if the tokens is not idle, that is, in its queue there are some pending requests, then we will follow the rule to release the critical section. Okay. That means that this token is with me, the token is not idle, that means I must have completed some critical section, now I have to release the token. Okay. Now, that there are rules for that, we will see shortly, that is what is to be followed in this case. Now, on receiving a request I SN message at j, we set RNJ I to max of RNJ I and SN, right. Again, this is what we were discussing just now, it is possible that Rnji and Sn differ by more than 1. It is possible, right. So, we take the max of the two, because we know that this is the largest numbered request that has reached us, Sn or I. Now, if Sn is smaller than this, what does it mean? It is an outdated message. If Sn is smaller than Rnji, that means that this request message is an outdated message request received out of order later than requests that were sent later. Okay. So, this is an, otherwise the max will come from this. If j has the token and the token is idle, then send it to I if Rnji is lni plus 1. Now, what is lni? Let us go back. Lni is the sequence number of requests that j executed most recently, that is kept with the token. Now, see, the token always has this data structure nice and well updated, because it knows which critical sections are being executed. It is always there when the critical section is executed. So, it knows which sequence numbers have been executed, alright. So, lni is the last request of I that has been executed, and if Rnji is 1 more than that, then it means it can only be 1 more than that, it cannot be 2 more than that. It cannot be 2 more, it cannot be 3 more, it can only be 1 more or equal, because at a time there can be only one pending request in each node. So, if it is more by 1, that means there is a request in I which has not yet been served. Then it will send it to I. Okay. All this if the token was idle, meaning that it did not have any other pending requests in its queue. Now, if there were other pending requests in the queue, then it is not necessary that we send it to I, we can send it to somebody who has made a request earlier, alright. So, if the token is not idle, then we will follow the rule to release critical section. Again we will see what those rules are. To enter critical section, very simple, if the token is present, just enter. To release the critical section, this is the releasing rules that we have been talking about for some time now. Set lni equal to Rni I. Okay. Why? This one has, process I has already completed executing its latest critical section. So, lni is equal to Rni. Now, for every node j which is not in queue, add node j to queue if Rni j is equal to lnj plus 1. Let us understand this correctly. We are updating the tokens data structure with all requests which the token yet does not know about. Token is maintaining a queue of pending requests. Now, when I was executing the critical section, there can have been some requests that have arrived, right. These have to be updated in the token. So, for every node j which is not in the queue, we add the node j to queue only if it is a new request. How do we make out it is a new request? If Rni j is lnj plus 1, if the sequence number of the request from j is greater than lnj, it can be greater by only 1 of course, then we update it in queue. Now, obviously, if the node j was already in queue, if it was already in queue, it cannot again get into the queue, because its request, there can be only one pending request from J. So, if it is already in the queue, that means that request has not yet been served, and it cannot spring up another request before that is served, right. So, if it is already in, yes, it will never come. So, if it is already in queue, then we do not have to do anything, then it already, the token knows that it has made a request, but has not yet visited that node, right. If it is not in the queue, then there are two cases, that the request that I have right now is an outdated one, which will happen if Rnij is equal to Lnj, or less than Lnj will not happen, because I will copy it from the token. So, then I will know, right. Otherwise, I will update it and add it into the queue.
J is not requesting, if some process is not requesting, why should I add it to queue?
No, this is only you are, see, if it is not requesting, then it will never, this difference of 1 will not come, then you will see that these two are equal. Okay. If queue is non-empty after you have done these two, then delete the first node from the queue and send the token to that node, right. So, you see fairness is guaranteed by virtue of the queue which the token maintains, right. Whenever requests come, they are getting added into the tokens queue, and the token is being sent to the first node in the queue. Is it clear? Right. Now, note one thing, when I am sending out the request message, I am broadcasting the request message, right. Suppose I knew the process which holds the token, even then I would have broadcast it. Why? Because the token can move while the message is in transit. So, every node should know about my request, so that they can update it on the tokens data structure. See, the node which receives the request updates it on the tokens data structure. So, to get myself enqueued, I am saying, hey, whoever has the token, please put my name in the tokens queue, right. So that the token in due course of time will come to me, alright. So, if you have any doubts on this, then we are going to take it up in the next class, and I will also talk about another token based algorithm in the next class. Right now, let us look at these features, that number of messages in this algorithm 0 if node already holds the token and there are no pending requests, and it is n otherwise. Why n? Because I have to broadcast, right. And then after that I do not have to send any messages anymore, I just broadcast my request and the token in due course of time will come to me, right. What is the synchronization delay? What is the meaning of synchronization delay? One node exits critical section and the next node enters critical section. The gap between the two is the synchronization delay. Now, the synchronization delay is 0 if the node has the token and the token is idle. Otherwise, it is maximum message delay, because the node which completes critical section sends the token to the next node, and whenever the next node gets it, it enters the critical section. There is no starvation. Why? Because the requests are queued up in the token, right. Okay. Right. What do you think about is this better or worse than the permission based algorithms that we studied? Is it better or worse than Lamports, Raikart Agarwala, Maikawas, or actually are we, or is there a trade off that this is good in some, that is good in some? Think about this, we will discuss in the next class.